Okay, for people joining this live stream, sorry we're starting a little late. I was in the middle of giving a talk to a group in the Netherlands, and they were asking really great questions, so I wanted to continue a little while longer here. So let's see. Well, this is going to be a working session where it's kind of like a little bit you're watching me do my homework. I am working hard on Combinators in preparation for the 100th anniversary of Combinators on December 7th, but also because I've realized that Combinators are yet another kind of analogy to a lot of things we're doing in the physics project. And so I wanted to explore them. So without further ado, let me jump into the things I'm trying to figure out. Let me just go ahead and run some of this here. I need to get started with this code. Oh, and I need to run that there. Okay. So let me start running some things here. Okay. So let me show you the thing that I first want to figure out. This is I'm going to bring up the smallest combinator that leads to growth. There it is. Let's just run it for 20 steps, for example. There's the messy thing it produces. So let me see. I've actually got some new, I'll show you a few new things I've figured out. Let me see here. That's not where I wanted to go. Hold on a second. I am looking for, actually, I have to show you guys something cool. So a question is, how do we visualize what's going on in this combinator system? So we can just look at the leaf count here, the size of these expressions. We could also look at something like the depth. I think that's what I need to do there.
Why don't we look at the number of unique subexpressions?
Yes, I just started doing that actually late last night. Let me show you that, because I just did that actually, and let me show you something, Max, that you haven't seen yet. Although you invented the idea that led to it. Hold on a second here. Okay. So what we need is this function toDag, which converts one of these combinator expressions to a directed acyclic graph. And I would like to actually add that to this code thing here. Let's see, conversions. I think I have a section here about conversions, combinator construction, combinator conversion. Actually, let's put in two functions. So combinator toDag, which is going to be this thing here. And then we also probably want, and by the way, Max, you have probably convinced me that I'm going to be a control 8 person from here on out. Of using, isn't that, so thank you for that contribution to my life and times. I'm sort of getting convinced that this idea of having initialization cells is sensible. It's all right, eventually you'll convince me to use Git as well, but that's going to take a while longer.
But the next step is to use command 8 and do code formatting by hand.
I hate that. I absolutely detest that.
Well, either that or improve the built-in code format.
That's what we're working on. Yeah, that's what we're working on. In version 12.2, that should be there should be an improvement there. Okay, so the next question is, how many unique subexpressions? What's the fastest way to find the number of unique subexpressions? Is it to count the union of the levels, or let's see, we want
I
to say,
guess. Well, unless there's some internal trick to do it. Because I mean, it should probably know if it does not duplicate subexpressions, as you say, then it should probably know already how many subexpressions there are.
it does know.
Of one. But
Oh,
I don't know if you can extract it.
I know how to do it. I know how to do it. Okay. I mean, it's a hack, but I know how to do it very fast. If we want to do it really fast, I know how to do it really fast, which is to use byte count versus leaf count. I predict, actually, this is a cool idea. So I predict that if we look at these things and we say we got the leaf count up there and we now say byte count, let me look at the documentation for byte count. I mean, this is a hack, so I'm not sure we really want to use it, but oh, actually, that's interesting. Byte count does not take account of any sharing of subexpressions. The result it gives assumes that every part is stored separately. The amount of memory. Well, so much for that idea. I think that thing that is obviously very fundamental to the internal implementation is actually quite deeply hidden. That's an interesting question, whether we could write a function that exists.
Well, maybe there is an internal function to do that.
I'm sure there is. I mean, share. Okay, so let's look at this. I mean, share. I don't know whether share. I mean, if I run share, well, okay, I don't think we're going to be able to solve this problem right now. But this is if I look at this, I wonder whether if I take that byte count, let's say I say byte count of hash over leaf count of hash.
Why leaf count?
That's the number of symbols. So that's,
yeah, but it depends on the size of the tree of how they would be related, isn't it?
why isn't the leaf count is the number of final nodes? You're saying that it depends on the structure of the tree. So how many nodes does the combinator tree have for these things? Let's ask that question. I don't know the answer to that. I should know the. Is that obvious? If I say vertex count.
Well, actually, it might be, because every next level just points to two subexpressions.
Right. So the number of leaves is equal to yeah, every node in the tree. Look, if we say let's see, I think it was called combinator expression graph, is that right?
Yeah.
Do I have it in, is it in code 02?
I believe so.
Ah, it is, but it hasn't been maxified.
What does that mean?
Done with control 8.
Well, that's not maxified enough. If it was really maxified, it would be a Parklet.
Right. Oh, this is still a mess, right? So Manu, you don't have a version of this that has these arguments straightened out. Is that true?
Not yet. No.
I think I have a version of a combinator tree. Okay. All right, so combinator tree. Oops, I did that here. Okay, so let's compare that to okay. This is now a question for Ed. What's the relationship between these two things? Is that 2n plus 1? 2n minus 1? Yes, that seems to be. So in other words, the vertex count in the tree is 2n minus 1 times the leaf count. Is Ed with us, by the way?
Well, it makes sense because every time you add the vertex to the tree, you decrease the number by 1 you decrease the number of roots by 1.
Right. Okay, so I want to show you the thing I was doing yesterday. If I say to DAG, these are the DAGs that you get. Okay, now what's more interesting, here, I'll show you. These are the DAGs you get for much larger sizes. Okay, so that's showing you with the common subexpressions. Is Ed with us? Is he?
So I'm right here.
Okay. Because what we're trying to do, one of the things I want to do is to actually prove that. So if we look at this leaf count here, you know, it seems to be increasing. If I say 100 steps or something, okay, it seems to be increasing, and we can look at okay, it has that weird form. If we keep going, there's actually considerable regularity to the structure. And the question is, you know, what is that regularity? And I think, Ed, you looked at this a little bit. And then can we readily prove from, for example, the structure of this DAG that this thing's going to go on forever? Okay, because yeah.
I'd say yes. Just try to say 300 and do the same plot.
We'll be waiting a while.
Oh, okay, never mind then. I didn't know these things.
Well, it's going to get pretty big. You can see it. I mean, although the ratio is...
The whole point is it does not actually get big. It has duplicated more times than necessary.
Mm-hmm. Okay, well, there we go. Okay, so those are the ratios. If we say list log plot, it seems to be exponentially increasing, right? Now, it's a little weird. What's the best way to get a fit to this, given that it's scalloping like that? And given we can see the ratios here vary between 1 and, you know, some value about 1.08. I mean, you know, what this suggests. Look, I mean, probably what I should do. Let's get rid of the first 50. Okay, so drop line 97, first 50, and then let's make a histogram of the ratios. What on earth can we say from that? What does that mean for what this average growth rate is? guys. I mean, what's the best estimator of that slope?
Why don't we just fit it directly?
Fine, let's do it. Fit the ratios. Well, the ratios are going to be that messy thing, but why don't we just fit this to...
Or do log of that, fit the log.
No, but the log is going to look like this. I think we're better off trying to fit A times B.
What means the log looks like the least log plot.
Oh, for goodness sake. Hold on. Let's see. Range, length 97. Length of percent 97. And then to be really stupid about it, let's say drop, comma 50, comma that, comma this, comma transpose.
So you need to say plus C in there. Because it doesn't look like it
Number of
starts.
variables is not equal to the number of... What is this saying? I don't know whether it needs, but why is it saying this?
Are you sure you're using the right function? Because there are also nonlinear model fit.
Actually, what I want to do is find fit. There we go. Much easier. Okay, so that's 1.023.
Might be better to do drop minus 50 for that first one.
Why?
Oh, that's right, because never mind.
Transient there. Okay, so this is saying it's, so let's plot 1288 times 1.023 to the t. T goes from 0 to 300. And then let's say...
I predict you need to add plus C. Oh, actually, hold on, maybe not. Never mind.
Okay, so now let's combine that with line 99. Well, that's interesting that it seems to be changing its slope. It's a little bit scary. Can we derive
Well,
that?
of course, it's changing its slope because in the beginning it's completely different.
You can kind of see that with the ratios earlier because they were steadily dropping at the top.
Okay, but can we derive the 1.022? I'm going to ask several related questions. I mean, I basically want to understand what is this thing doing, right? So I don't know whether these are useful. Oh, Max has proposed that we look at the number of distinct objects, and I did look at that for this thing, and I'm going to show you that. Let's see. Okay, so this is, I don't know whether this is the best way to compute it, but what this is doing is that's looking at the length of the union of all the things on all these levels. Okay. Okay, so this is the number of distinct subexpressions. Okay.
Okay.
And that looks quite uniform. But if you now say, okay, so now
it basically tells you the number of upstream updating events per event, as far as I understand. Well, roughly.
I understand that. Because Okay, so the claim is
because
that
if there are no cycles, then, well, actually maybe more complicated. But ordinary events, they produce a fixed number of new expressions.
well, how many is it? I mean, so what we've got is the S. I mean, we've got the particular rules, right?
Well, it's no more than 3.
Well, let's see exactly
because
how
there
many.
is a head, the argument, and the entire thing.
Right. Well, so this is x of y of x of z, right? Okay. So how many
Is
new?
that x of z of y of z? I'm not sure. I need to double check.
X of z of y of z.
Okay. So how many new expressions are created by this thing? So just saying we've got these 3 expressions here.
Oh, wait, how do you count that? So we have.
I mean, they might not be
3.
distinct.
Fair enough. The expressions are not x, y, and z. The expressions are s of x, s of x of y, and s of x of y of z on the left.
Mm-hmm.
X of y, x, y, and z don't get created.
Well, so in particular, let me draw what these are. Okay, so what we've got, if I say 2 dag of this, okay, let me actually write this out in a more complete way.
To check how many are created, you need to plot the combination of them on the right.
Okay, I see what you're saying. Okay, let's do that. Hold on one second. Okay, so generically, I need to make this layered. Okay, so that's the generic story there. But now, so what does that tell us about how many things are created here?
3. Because the 3 vertices on the bottom are already there. The other 3 are not there.
So how
they
can
might
there
be there, but they might be the same as something else that is not part of this rule, which is what makes it complicated.
Okay, but how come there's a difference of 5 here?
Because there's an upstream update in events as well. Each of which can create up to 1 new expression.
So you say this could be less than 3 if some of these are shared.
Yeah.
So, all right, but let's take a look at this thing. I wonder if we can continue it any further. I mean, it's really a shame that we cannot. I mean, could we write a memoizing combinator evolve list?
What
I
do
bet
you
we
mean
could.
by memoizing?
Where every shared subexpression, where the update event, so we have a combinator step, right? Why not just store what we already computed? If there's so much, right? So we have a combinator step here. We've got
It takes the entire expression as an input.
Combinator step takes the entire expression, right? But what I'm saying is, would it do us any good? I mean, can we directly operate on the DAG and just update?
Well, of course we can, but it's a completely different way of doing it.
Someone was asking here, Perkinger was asking what the transitive closure of these things is. Let's work that out. Well, I think these are, actually I'm more interested in the transitive reduction of these. Let's see what that looks like. Transitive closure is going to be a big mess. Or are these are they trivial under transitive reduction? They are not at all trivial under transitive reduction. Is that obvious?
Well, the problem is it loses information. There are really two types of edges here, and we cannot really mix them up. Because, I mean, this is not really a graph in ordinary sense. This is just a data structure, which we are drawing as a graph. And it's important in the data structure, which one is left and which one is right.
It seems like it does give some information to see this transitive reduction. Let's see what it looks like for, just for the hell of it, for one of those big ones.
I realize this is the same one that I studied earlier.
What the heck? Okay, I want to see that, but just a second. What the hell does this tell us? What does that tell us? Okay, I have a collection. Let me show you what I got yesterday. I have a collection of non-terminating cases, and there are those. And I'm sort of inclined to try running these for just for the hell of it. I'm just for curiosity. I want to see what the transitive reductions look like. Where is that? Drat. Help. I'm just trying to find my computation of these. Here we go. So these are the size 8 cases that don't immediately terminate. Well, don't don't appear to terminate. Okay, let's try running this. Oh, that's just the regular graphs. I now then want to do the transitive reductions. But a question here is which of these, no, what do we learn from these, and do these imply, actually what I want to do is I want to show this together with, here, let me do something here. Let me show a little bit of technology here. What's this doing? Oh gosh, how do you switch off? Mano, maybe you know this. How do you switch off the dynamic locator stuff for graphs?
Oh, I don't know.
Okay. Here we go. Okay, so let me just show a piece of technology here that's relevant, and then let's say, because I want to look at these. I'm going to show a few different aspects. Hold on here. Oh, and I also want to show the that differences plot that I was looking at before. Hold on. Now you'll see what I'm doing. Okay. And here, what I want to do here. Oh God, this is the same thing that happened to me yesterday. I think this cell has just got an absurd amount of for some reason, it's got an absurd amount of dynamic location stuff in it, which it doesn't need because it doesn't have any labeling. And it's just slowing everything down like crazy. I think it should be reported as a bug. Oh gosh, it's just crazy. It's just absolutely crazy. Look at this.
I'll report that.
If you can pick up this, well, I'm going to delete that cell here.
Okay.
So I think I might be able to say here, okay. All right, let's try running this. So, oh, come on. Help. Don't tell me this is what I get for running on all these computers. It's probably not going to be easy to kill it. Okay, let's step plot. Length of union. Oh, silly me. I got that in the wrong place. Okay, let's kill this off. Okay, let's go ahead and that again. And did I end up putting the DAG? I did in the conversions. Combinator to DAG. All right, let's try this again. Okay, this will have to relaunch all the kernels.
Is combinator to DAG something you want in the function repository?
Yes, I think so. And it needs to have the vertex labels, arrow automatic case, and so on should work, which I had to do by hand up above.
Okay.
Okay, so what we're going to do here, we're trying to run, let's hope this doesn't say, hopefully we can parallelize. Did you write parallel map monitored, Max?
Well, yes. Although it never meant to be usable by anybody except for me.
What does it mean when it says 4 out of 46? What's happened at that point?
So let's see. Well, I think it finished 4.
I see.
Well, yeah, because if it started 4, it would be immediately, all of them with your machines. The only problem is that if some kernels crash in the middle, then it overcounts. But it doesn't seem like it's happening here.
I don't know why this is going so slowly. And what I'm trying to do here, as you can see, is yeah, I mean, I'm going to 100,000 maximum size, 100,000 maximum steps 1,000, and I'm trying to get a picture for all of the different cases that we know don't terminate at size 8 of what happens, because then I want to look at them to try to understand which of them are sort of truly sort of random and which of them have a regularity. I mean, like this, for example, surprises me at how random it looks. But maybe this is just a bunch of non-commensurate, periodic pieces. How would we tell that? Oh, this is so painfully slow. I wonder what it's doing. Why is it so slow? Maybe I just cranked up those parameters to such large values. I should have run for slightly smaller cases, but I think it'll be useful to see what this does, assuming it actually comes back and it doesn't just get stuck.
Well, the weird thing is that it seems kind of sequential, because it should be running all 46 simultaneously.
I'm sure it is. I'm sure it is on different machines. But some of them are more, some of them are easier than others, and many of them may be of equivalent difficulty. But let's just take this. Let's start up a new kernel, and let's just take this one and look. Okay. I just want to take those numbers and just have a little play with them, see whether we can understand what's going on. So, these are the number of unique expressions. Okay, Ed, you're on. What do you do with these numbers? So let's say,
yeah, that's the one you sent earlier.
Did you figure out something about it?
No.
Oh, you figured out this is your thing for the whole shebang. Okay, we'll worry about that in a minute. But let's well, let's see if we look at position in that of 0. Oh boy.
I can split it into 2. The number of created expressions, the number of deleted expressions.
Oh, you mean by looking at successive? That's an interesting idea, Max. That we can track over time. Yeah, the number of expressions that show up. Okay, let's write code that does that. Okay, hold on. Let me just see what's happening with this guy. Help. It's predicting in 8 minutes to completion. Well, let's go ahead.
The predictor assumes there are a lot more cases and cores, so it doesn't help in this case.
Okay, let's write something then that can do that thing of knowing which subexpressions are Okay, so what we're saying is, in this combinator to DAG thing, we're counting subexpressions, right? Combinator unique expressions, but what we want to do, okay, so here, let's, oh gosh, how do we do this? How do we evaluate this code 02? Will the following thing work? Oh my God. That's a hack within a hack. No, I'm not going to use that. That is too crazy. What I meant to do was this. Is it not the case that the initialization cells are, if I say get, won't I run the initialization cells?
I'm not sure.
Maybe I need to say notebook get. Let me read the documentation.
You might end up running all of it.
No, I need to look at what get does.
Well, get just evaluates the code as is, which is a notebook expression. So it's not supposed to do anything.
How do I get the initialization cells? That's crazy. I thought you could just say get of the notebook and it would run them.
Well, to be fair, that's a very obscure use case, because by the time you're loading code from another file, it should really be a package.
There needs to be a do what I want function.
Hold on. Let me just, hold on 1 second. Okay. Oh dear, this is really not a good idea. Well, it's gotten to 21. Shoot, and it keeps on estimating longer. This is super painful. Well, do we keep it running? Yes, I think we'll keep it running for a little while longer. Okay, so let's go back over here. I mean, I can clearly fix this. Okay, I'll do this. I don't really want to do it this way, but I will. Let me go ahead and say notebooks kernel delta 2. Okay, I'm going to say notebooks kernel default so I don't mess that up. Okay, so now I can say combinator evolve list of the one we were looking at up here. Okay.
That's the one I sent code for, by the way.
Yeah, I know. You sent code for the, okay, so let's look at this. Let's look at 10 steps here. And then what we're going to do is we're going to say for each of these, let's get all the subexpressions, right? So then what we want to do, we want to get all the distinct subexpressions, right? So that is otherwise known as
Should we have a function for it?
We will. Okay, but that's going to get those things. But now what we want to do is to make a graph that shows which are new, when there's a new one versus when there's one that just comes from before.
Yeah, just a partition to one and then two-way complement.
What do you mean two-way complement?
Well, the two complements you can do in both directions. Complement AB and complement BA.
Yeah, I know. So that's a. Oh, I see. But what's your point about that? I mean, can't we make a graph that shows the things, arising and disappearing, or is that a bad idea? Well, you're saying we take this. What's that? You're saying we simply take this, and we say,
well, we can make a graph out of all of them. Single graph including all of them, but that's not what you're trying to do.
Right. But what you're saying is, I mean, this is a symmetric difference, isn't it?
I guess.
Well, let's just call it SD because we don't really know it's the symmetric difference of A and B is length of complement of, let's see, that's the number that disappear, right? That minus or what? And then length of complement BA. Okay, so now this is SD triple at that. Okay, so that's the number of things that appear versus disappear. Okay,
yeah, now we can transpose them and see if we can understand each one.
Okay, well, let's try running it for like 100 steps. Okay. And so what your claim is that the final result is one minus the other. Is that correct? Which one is minus? The first one is minus, right?
Did you do a list line?
Yeah, I will. Hold on. Let's just do this. And then let's say great. They're always differing by one, I think. Is that right?
No, not at all. I think they're different by the thing we measured previously.
Well, let's see what we did measure previously. So this is this thing here.
Which makes sense because the change in the number of expressions is the number of created ones, the number of deleted ones.
Yes, I agree. But now what I'm suggesting, by the way, in terms of maybe I'm confused, but what I'm suggesting in terms of the computation is that we just use the cache of what happened to one of these expressions, right? But maybe I'm wrong, that's what we can do. Okay, so those are those. That's rather uninspiring, Ed. I mean, we can try looking at the differences of those. Let's try that.
Well, it's telling us there are more and more upstream updating events every time.
I don't know what to make of this. I mean, I don't know what to make of the fact that this is, okay, let's just take, okay, what is that function? I mean, there's no, you know, it's surprising if this thing doesn't have regularity. It really is surprising, but it's not impossible.
I think for this one, we're still seeing initial chaos, and that we need to do more steps to start having an appreciation of what's really going on.
Okay, well, let's do it. Let's hope that this isn't competing too much. Oh, shoot, it's still running. It's up to 35 out of 46. I think it's going to make it. Here, oh gosh. I mean, that's the problem with, okay, is it obvious how to make this faster? By using, I mean, my idea is, I mean, I guess I wonder what's slow and whether what's slow is finding a thing that matches. Oh, well, there we go. Okay. You know what? I need to start modernizing. All right. Is that periodic at the end? Let's find out. So 100. That's crazy. Wait a minute. Okay, so wait a minute. Let's look at these things then. So they don't appear to be periodic. Okay, what can we say about this? What is this? Let me just check that these are what we think they are.
Try applying length split on each of those.
Yes, that's what I was thinking. Because look at those things. They just get longer, right? Oh my gosh. Well, let's see. Do we do another well, let's look at these anyway. Well, that's beginning to show at least some regularity. Right. I mean, see, the question is it completely regular, or is there some little piece of randomness hidden in it? I suspect it's pretty regular.
It started to become regular, but then got broken at the end.
Yeah, it looks like it's completely regular after 150 steps.
But what about the last step?
No, that's okay. The last step is just because it doesn't have it doesn't get to the next place where it can do the split.
Oh, I see.
So well, what can we conclude? Is there more detail that we can get about expressions created and so on? Like, for example, we could get the size of each expression that's created, right? In addition to the number, we could also plot the size of expressions created. Couldn't we? So up here, well, you say it takes 150 steps before it starts to be regular, but for each of these, we're partitioning. Okay, so in the complement thing, we could do a leaf count. So for each of these, wherever I defined SD here, so I could say here, instead of length, I could just say length of complement. And for each of those, we could say leaf count. By the way, we don't know if expressions are created and then destroyed again. Okay, so this is showing us, wow, these things get big. All right, what's the best way to visualize this? For each one, I think what we want to do is this. We want to say, transpose that, then what we're going to get is each of these, and then what we're going to say is a map indexed for each of those, map indexed of first of hash 2, comma hash 1, onto hash at level 2, and then we want to map that across this, and then for each of these we want to say list plot. I claim. Actually, we want to catenate to throw in there for good measure. All right, let's see what happens if I do that. Yeah, there we go. Okay, so what that's showing, it's not very informative, actually. It does show these weird, look at that, these weird regions here. Do you see that? Sizes of newly created expressions. So what this is, unless I got it wrong, did I get it wrong here? That's the size of the newly created expressions at each step.
No, it looks valid.
What on earth are these things where there's a seismic shift every... Well, the question here is, okay, how would we prove that this thing doesn't terminate, right? In other words, how do we prove that there are always fresh, is there something we can see from this plot that shows us that the thing's never going to terminate? Or something like that. Some repeat here. Like, for example, if we could show that there's a repeat, that at this stage you get expressions of this size, then this one you get this size, and so on, and that will always repeat.
Oh, the size is not enough.
No, I understand.
We need to show some kind of recursive relation.
Right.
I think you get that earlier with the recursive behavior we saw in the simpler graph.
The thing that's most bizarre are these glitches every so often. I wonder how frequent those are. I wonder what can we measure? What's a good way to measure where those are?
Now this is the size 100 case. I think you'd see things better in the size 300 case.
Let's compromise. Let's go to 250.
Mm-hmm. You just need to go beyond 150, I think, for this one.
I mean, the problem is this is only a particular updating order, and there are other updating orders where this behaves differently. Oh, this is driving me crazy. This is at 42 out of 46 over here. I mean, it should be bounded because it's only got to 100,000, well, max size of 100,000. Why is this taking forever? Did the other one take a long time as well when we did the other thing up to 300 here?
I remember it took like 40 seconds.
Well, this seems to be taking even longer. Because what I really want to do is I want to use these up. There we go. Okay, let's take a look at Ed's theory. Well, that is awfully repetitive looking, isn't it? Qualitatively, at least. I mean, it's not totally obvious it's any more repetitive than those scallops that we saw to begin with. I mean, by the way, the simpler plot, by the way, is just to ask, the much simpler plot here, you just do it for 100 steps, for example, is just to ask for union. Okay, so each one of those, it's leaf count of that union. So that's the total from both sides. What are these things here? Oh, those are expressions that are neither created nor destroyed, right? That didn't change from one step to the next. Making sense?
Mm-hmm.
Well, okay, so what we believe here, we don't really understand why why we don't see regularity in this, but we believe there is regularity in this.
That's the initial chaos there. That's the one with 300. That's a different one.
Which one is the one with 300?
Never mind. I think these are all the same one.
Right, so you're saying that above 150 or so, this starts to be very regular.
Yes.
Okay. Okay. All right. Well, then let's look.
And before that is chaos.
Yeah, I don't care about the before that. The transient is not interesting. Okay. So, what I had done previously, I have all these cases where, and what I'm looking for is ones where, that's why I'm trying to get this stupid thing to run here. Well, let's go back and look. Okay, so I automatically generated this notebook of partial results. So this is, I guess one of these is that's ratios, a log, and that's the depth map. Although I think this depth may be wrong. Okay, so our mission is to understand things like this, right? Does it become regular or does it just make a mess? Right, what do these different things do? Can we say what they do? Like that one is going to in fact die out. That one, I think I asked you about, Ed. Did you crack that one?
This one, that's the one. Yeah, that's the one with the check marks I mentioned.
Well, can you give a formula? So does it grow like square root of t? Am I right about that?
Almost, but not quite.
I mean, almost, but not quite. In some lim soup sense, does it grow like square root of t?
Yes. Yes.
Okay.
But the actual formula will be as complicated as the one I put into the chat.
Well, the formula you have here by the way, if I know the positions in the tree at which these rewrites happen, is there a good visualization of that?
I don't know.
Well, no, there's a bunch
You
of
can
zero.
show them on the DAG.
Well, it's fair, Danny, but I mean, the point is that there are sequences of zeros and ones which could be turned into binary integers and could be turned into, a location. This is a mess, Ed.
It's a messy function. But that perfectly describes the behavior of the one long sequence you sent.
I think I simplified this slightly. I mean, this is the tail, this thing you're calling coded, right?
Right.
Wow, that's complicated. Really? This is it? I mean,
this isn't the one for the check mark. This is for if you evaluate that, it's really fast. You'll see the sequence that generates the sec extended.
Do I want to say scaling function arrow log? Doesn't look like it, does it? Oh my gosh, this finished over here. What do you know? Amazing. Okay, let's see if we can generate the nice thing here. Okay, hold on here. Okay, here goes. Why is this taking a long time? What has this got in it? What did we do? We made a mistake here. Something is crazy.
Well, it has 200,000 size expressions.
No, it doesn't. That isn't the
Oh, I see. We convert it. Okay, fair enough.
did I get something horribly wrong here? That graph. What is going on? Why is this taking so long? It should be instantaneous. Oh, great, and it's not interruptible. Oh, yes, it is. Okay. Oh, no. Look at that. I think it just killed the whole thing. Oh, no. Help. All right, I'm going to run a smaller version of this just so we can see something. That was horrifying. All right, let's go down to 25,000 steps and length 500. Okay.
Actually, maybe also do just do the first two just to make sure it works.
Well, I predict this will be quite fast. He says, optimistically. I just want to get a thing where we can just start checking off these different cases and see what they actually do.
So what are the behaviors we can get out of these combinators? They can halt, they can have a transient, they can be chaotic.
Yeah, well, yeah, and they can grow in a way that we don't fully understand.
Can they ever start looping?
Yes, I've seen examples with other update rules, where with other evaluation orders, where they go into a loop. Yes.
So those are the 4 different behaviors?
No, I mean, the animals are always smarter than you are. They can probably do all kinds of other weird things. They could probably go for, I don't know. I mean, if you say, you can hide a lot in, I mean, they can increase, but exponentially, and this and that, different rates and so on. How is it so slow? Why is this so slow? I just don't understand why this is so slow. Even with max size 25,000, it shouldn't be slow. Am I getting this wrong? Combinator to DAG.
Another problem is that output is pretty large.
I don't think it's that large. I mean,
But it was so large that it, well, I don't know why it crashed the kernel exactly.
It's very frustrating here. Because I was running these before and they were really quite fast. Maybe this combinator to DAG thing is really slow.
Can you check how much internet connection you're using?
You mean onto the parallel computations?
Yeah,
Not easily, no.
why not? You can just like check activity monitor.
How should I see? What should I see under network packet?
It's 25 megabytes per second. So the question is, who does it?
Well, who knows?
Oh, that's quite a lot.
Okay, but many of these machines are local. I mean, you know, these cores are. What is going on here? I mean, the other possibility is that there are some machines that are running rogue that have they're just like slow as molasses because they're running because they've got a bunch of rogue processors running on them. Let me see. I've got a program for checking that here.
Oh, 200 megabit would saturate Wi-Fi.
It's not Wi-Fi. I have fiber optic interconnects.
To the computer?
Yes.
It's.
I'm not using Wi-Fi to connect between computers. I mean, partly because this was set up 20 years ago when Wi-Fi was not as fast as it is today, but
because fiber optic 20 years ago, really?
18 years more accurately. And light is still traveling at the same speed as it ever was. No, seriously, I forget. I think it's been redone since then. But okay, why is this so slow? What is going on? Why is this so slow?
Do you want me to grab Roger?
No, it's nothing to do with him.
Okay.
Okay, I'm gonna do up, and now it just finished. Okay, let's just get a sense of this. Let's just say byte count.
Can you save it somewhere before running the next cell?
Okay, why is the byte count of GGG taking forever?
Well, because as we figured out, it's not really the byte count.
It's 18 gigabytes.
Can we really not do the real byte count?
What happens if you do byte count map to GGG? Is there one that's much larger than the others?
This is crazy.
Well, it has to enumerate sub-expressions to do this.
Yeah, there's a bunch of gigabyte-sized ones, some 2 gigabyte ones, and so on.
The second to the last one looks nice.
Okay, reluctantly, I'm going to do your suggestion.
Can you check how much memory it actually uses? I mean, the entire kernel.
It might be worthwhile to take those values and the original list and do transpose and then sort by size.
No, let's not do that. Let's just do this.
Okay, so are you sure it's doing? I mean, it's either showing with subexpression expanded or actually not storing them multiple times. Because these two seem very close.
Let's just check that. Okay, that's super fast. Okay, so here, just to understand what this will do. What the heck? Why is that slow?
Wait, you have GGG in it as well at the end.
No, but that's okay. That's not the relevant thing. Okay, well, we can at least start off with this, even though this is rather impoverished. This is showing us at least the beginning.
Needs to have some labels.
What?
It needs to have some labels.
Well, okay, I can tell you what these pieces are. Okay, so this is, oh God, that's wrong, by the way. That depth is wrong. That's, so you can ignore that one. That's meaningless. This is, so let's just have a little look through here. Okay.
What's the second to last one? That's the one that had a really small byte count in the big run. Oh, that one is really simple.
It terminates. And that's its final state. Okay, so some of these, that's the log.
Wait, why does the final state has two leaves? Don't we only have S? Oh, we have K now. Okay, fair enough.
Yeah, that one has K as well. Okay, so let's take a look here. Okay, so this one, that one holds. Okay. So this one looks very regular, and that makes it look regular as well. Right, so maybe that one is one we can study. Okay. This one looks quite irregular. Okay, so that one is question mark irregular. And here, if we go like to 5,000 or something here, okay, that's what that's doing. Now, well, okay, so let's keep going because I want to figure out which ones show kind of real randomness. Okay, look at this one. That's interesting. Look at that. Oh, that one is a terminating one. I recognize it. So is that one. That one looks kind of interesting. So let's go to size 5,000 there, for example. Oh, that's that guy. What's interesting is that that plot is as comparatively irregular for that case. Right, I mean, that thing there, let's take a look here. What the heck? Okay. That's what this turns into. That's odd looking. I mean, that's odd that it has, I see, we're looking at the transient there.
Oh, by the way, the gap between each of those high points is an odd number that they're increasing odd numbers.
Okay. Okay, so the question is here, okay, so let's look at a few of these others. Okay. So what do you think about this one? Is this one doing something random, or is this doing something that's going to become very regular? Let's try 5,000 there. Okay, great. It's hard to tell what's happening here. I mean, I can, well, let me just go ahead and do the scaling. What can you tell about that? I can't tell anything. I mean, if we do the differences here, that's pretty weird. So we up to 1,000 steps. Let's try going to 20,000 there. Actually, we need a plot range all. And let's list step plots here. Okay, what do you think this one is doing?
Still too chaotic for me.
I think it's showing some regularity, but the question is whether these things basically show. Well, that's interesting that when I did double length, this didn't really show. Yeah, I think I looked at this one before. This one, when you double its length, it's basically showing a self-similar object. Oh, that only got up to 200 there. If you double the size, so I think this is increasing. Is this increasing exponentially, or what is it doing?
Yes, that's what it. Yeah, I think you're right about it. It doubling like that. Yeah, that does seem to be a fractal pattern.
But let's take a look at what can we see it in more detail? I mean, if we just look at this differences of leaf count here, can we explicitly see that those peaks are like doubling in size or something? So how do we find these peaks? We find things which are, if we looked at the second differences, we would find things that are more bigger than their previous thing. Well, not really, because of those zeros there. Oh, let's look at the running max. How do you define the running max? Max, how do you find the running max? Is it a fold list of max?
Max ran away.
What?
Max is still here. But if you're talking, we can hear you.
Yes, I am here. Well, we're getting partitions.
No, here we go. Look, this will work. So if we're finding, that's the running maximum so far, right? So what we need to do then.
Oh, I see. Okay.
Is that if we do list step plot of that, there we go. So now the question is, what is this doing? Is this exponential or not? And so what we want to do is look at the positions of those big jumps. So how do we get that? We say, can we use split by? No, I don't think we can. Do you understand? Okay, so let's also see what that's doing. 734 to 1450. Oh, for goodness freaking sake. 732, is that anything reasonable? Grumble, grumble.
There's also 716.
Well, it's 1.98. It's very close to a factor of 2. All right, so that's very close to a factor of 2 increase. Okay, so those double, but now the question is, how long are these runs?
Length split.
Well, it's not going to work because it's going to have a same by. Right, so split by. What is split by? Runs it when give the same value, splits list into sublist when. Does split have a second argument which allows you to have a same test? Yes. Okay, so split, go ahead. Mano, did you have something you were going to say? Split this, and let's say #1, abs of #1 minus #2.
I thought you could do this with first position, mapping across the union of cell 100.
Let's try this for a second. Okay, so length of this. See, I'm very suspicious about these little glitches. Okay? Because, you know, this is what I've seen in like 3n+1 problem type situations. These things where it's almost completely regular, but not precisely.
Right. A lot of these have been increasing by 1 or 2 each time, which is why they become really complicated to make a nice, clean formula.
Right, but the question is whether a formula is possible, right? Because there may be ones where there isn't really a formula. You just have to work it out.
Mm-hmm.
That's why I'd really like this S7 case that we were looking at before. I'd really like to see whether we can just get a formula for that one, even if the formula is a mess. All right, so that's this one, which seems to have, you know, almost regularity. Like this guy isn't. What the heck is that going on with that one? Let's say that's that same one again that we've already seen below. What about this one here? Oh, for goodness sake, what is this? Okay, what does that mean? What is the asymptotic value of this thing? So I don't think it's an exponential. Do you agree? I mean,
Yes.
So the question is, what the heck is it? So I think what we want to do here is probably to say, let's look at the differences here, which is one of these things there. So let's look at this differences. Oh my gosh. Well, that's fun, at least.
4, 5, 6, 7.
So what do you think? That means those things are getting further apart linearly.
Right.
And they're growing linearly. They're growing linearly and getting further apart. So what does that tell you?
That it's regular behavior, but semi-complicated because you.
I know, but what's the asymptotic behavior? Is it square root? You're going up linearly.
Mm-hmm.
Okay, so this means this is.
It's a quadratic increase.
What is the original thing here?
Right.
Why? Because this isn't linear. If this was linear, this will be quadratic. This isn't. This is a square root.
Right. Mm-hmm.
So if that's a square root, what is the integral of the square root, basically? My God, I'm actually going to do an integral. I can even do this one by hand, but I'm going to do it by machine just so I get it right. So that basically means this claims that this is a 3/2 power. So if I were to look at that on a log-log plot, what do you know? It's linear on a log-log plot. And above about 50 seems to be in a straight line. Okay, so that's the 3/2 power, probably. Okay, let's keep going. We're doing well here. I like this thing. That just looks nice. What do you think about this guy here? Well, that one looks like it's going to be very straightforward after a certain transient. Spluff. Okay, so scaling functions arrow log. Okay, I don't think that's an exponential. So let's look at log log. But I'm wrong. I don't think it's a power. Right, so let's go to 10,000 here. What the heck is this? Or does it perhaps terminate? Well, I don't think it's either of those, right? So let's look at the differences here. Oops, what is that showing? Okay, so the difference is there. Once again, it's a square root story. Do you agree?
Yes, I do.
So given that, why isn't this showing linear here?
Because it's also the number of pieces in each part is increasing and the size of the parts are increasing, so it's not quite square root.
I don't buy that. I mean, let's see. What do you mean it's not quite square root?
It's slightly more complicated than the squares are basically sum of odd numbers. This is more complicated than that.
But look, Ed, if we look at the asymptotic growth rate here, what is it? Right, see these glitches, these things here, they seem to be going up by a constant amount. Mm-hmm. And the distance between where they're going up.
Right.
Isn't the distance, if the distance between where they're going up is linear and they go up linearly, that isn't asymptotically a square root. But these are the differences. So why are the differences? Do you get what I'm saying?
Mm-hmm.
But anyway, that's clearly very regular.
Right.
Let's try some of these other ones here. Gosh, these systems are weird. All right, let's try this sort of weirdly scalloped thing.
It might be good to take what you had down below and just copy it above, and then you just paste in the different combinator.
Well, hold on a second. I can do that, but just a second. Okay, this is an interesting one. Let's see what this does. Oh my gosh. Just when I thought we weren't going to find anything non-trivial. Well, that looks like it's just exponentially scaling up, doesn't it?
Yes. But there does seem to be order there.
No, I know. I mean, it seems like it's just exponentially scaling up. So this one appears in constant time to be doubling its height. So therefore we predict that this thing would be exponential.
But not quite. If you look at the second to last, you'll see there's a slight jag in the second step, and that is, oh no, it is in the previous ones.
So this is the exponential case. So I think this is an exponential.
Mm-hmm.
Okay. What's surprising so far is that there are no really, let's try this one here. You know, all these guys, after a fairly long transient, seem to do something fairly simple.
Yes, that's what I'd notice as well.
Maybe it needs to find a good head, and then that head produces regular behavior in this updating order.
Yeah, but that's surprising that the thing it's surprising. I mean, I would have expected that there would be ones here that would lead to bizarrely how regular is this? Somewhat, but not very. Let's try some further, try going further with this. That's a little odd. Is that periodicity or is that not periodicity?
I think it is in groups of 3 high points.
So you have to be a little careful because some of these things, they really do. See, sometimes there's an overall behavior, and then there's some detail beyond that. I mean, do you think this is? It's not so obvious to me. It looks fairly regular, but I wouldn't be certain that there aren't. I mean, the question is this lump just some multiple of that other lump there? And we can see some sense of that by saying
the range like 300 to 350 is very similar to the range 400 to 450.
okay. Have we seen one like this one before? Okay, what's this guy doing? Presumably those are increasing exponentially. That's what it looks like.
Yes, I'd say so.
So if that's the case, if we say yep. Okay, are there any survivors here of ones that look complicated and haven't been crushed yet? This one is a partial survivor. Oops, that's not what I wanted to do. Is that linear or what? Oh my, when I thought we're finding
That looks pretty regular.
But what does it mean? What does this mean? This is another square root, isn't it?
Yes.
That growth.
Mm-hmm.
So that means that this thing here better be a 3/2 power law. Quite possibly. All right. These are like dropping like flies. So let's try this one up here. Oops. So right now, we don't seem to have any great survivors yet for something that is truly doing something really complicated. Or do we? Let's just take a look through here. What about this guy?
Well, some of them we've hand waved that they look like they're probably regular, whereas where others are, it's obvious.
Yes. Right. So some of these, okay, so let's look at this one, for example. That's another one of those pokey ones. I mean, they usually don't have very many different ideas. These things tend to be very, there's a small number of ideas, but then there may occasionally be one that has, oh, for goodness sake, what's that guy doing? See there, I thought it was just going to be exactly the same as the one before it, but it's not.
I don't see
Looks
anything.
like, what's that?
I don't see any sort of regularity there.
Well, what about that thing with that? Well, I agree. This one looks complicated. Let's keep it going a bit. So well,
But
there
that
is
looks
some
like
regular,
something.
except that thing there does not occur yet before.
Right, it's getting a little bit, that tail part looks like it's getting slightly more complicated each time.
Which tail part?
Oh, right after the big spike, then there's
Yeah, I agree, but now I suspect what's going to happen with these is that they're going to have, as I say, 3n+1 like behavior, that they're going to be fairly regular but for one little twiddle. But it may also be that the indicator of looking at the leaf count is not adequate.
right.
And for example, if we look over at these plots here, for instance, let's just do that for this one, for instance. Whoops. I need to find that SDX thing. Oh, whoops, that was in Delta 2. It's sort of regular, but not precisely. Wonder if it looked better without the log scaling. I don't know what these are doing. As I said, there could be more structure going on internally that we're not seeing, at the level of a leaf count. Oh, gosh.
Would
Okay,
it be
so
useful to look at the sub-expressions themselves that are being generated at each step and whether they're like contained in whatever's created throughout the updates?
I don't know.
How large is that notebook, by the way? As in megabytes or gigabytes?
I don't think it's very large.
Okay.
Why are you asking? I mean, I'm sure I can send it to you.
Yeah, you could probably send it to the whole group.
Right. Boy, okay. So I mean, my tentative conclusion here. See, what really is I'm suspicious about is I'm concerned that at least one of these is like a Rule 30, so to speak. A lot of these are kind of on the edge. They're not obviously simple, but they're not obviously, they're kind of like right at the edge of what's easy to explain.
Oh, I would try to rank these by where we understand what's going on. Like with 14 there, you can actually point exactly where the chaos stops.
Right. So there's a lot where they kind of go into a sort of cycle of behavior.
Mm-hmm.
Now, some of the ones down towards the bottom here have both S and K in them and might be more complicated. It's unclear. Maybe we could try. What's that one doing? Oh my gosh. Great. It's like an integer exponent function or something. What do you think the integrated growth is going to be like here?
No idea on that one. Looks like the ruler function.
Which is basically an integer exponent function, isn't it?
Yes, I think
Oh,
so.
I know this guy. I know this guy. This guy dies out. Yeah, this one halts. I think. Let me just check that, but I'm pretty sure it does. Yes. Actually, I just want to check. We can live very dangerously here, and we can just do this. Or is it going to crash? I don't know. Nope, that's right, 1958. That was a personal friend of mine from before. Okay, let's look at this one here. Oh, for goodness sake. Probably that's become something simple, but it's a little weird because those things are, it's extruding some of those, but how many of them does it extrude? Oh, wow. What's happening there? Look at that. These things are so weird. Oh, look at this guy. I think there's nothing very simple going on there. Ed, your comments? That looks like it's a complicated one.
Is it easy to go with more steps than that?
Oh, we'll find out. Well, let's also look at an indicator. I don't think this one's going to resolve. I think this one is a
Because with a lot of these, you don't see the behavior until 150 steps or so. That's 250 steps.
I don't think this one is going to resolve. Let's go for big time. Let's do 500,000. I think this is our first bona fide Rule 30-like creature. I don't think this one is going to resolve.
No, actually, if you look at, you see there's a level of 4 spikes down below, and then there's another set later. You've got 4 at the same height. Yeah, there and there.
Yeah, but look at this. That's different. Well, there's 2 more of those. See, again, the problem is unless you really, really crack it.
This one's going to die out.
Maybe it's going to die out.
If this behavior that we're now seeing continues, you see there's near the end there's it ends with a set of 3 spikes, and then there's 2 below, but those 2 below are basically that just means that this behavior might change after another 800 steps.
Max, what's the chance of being able to write something that runs this much faster?
I think the chance is pretty good.
Can you try to do it? I mean, and is it tolerably simple? I mean, so I think, I mean, is there any way we can cache at top level here? Is there any way we can cache subexpressions?
I'm not sure. Well, it really is a low-level code to make it reasonable.
I'm not as convinced as I might be about this thing.
Yeah, it looks like it broke. The set of four at the same level kind of went wild.
All right, so we have a tentative thing here. Now I'm curious whether if we look at our indicator, if we look at this indicator here, that's way too early to tell. I don't know how far we can get with this. Oh, look at these. They're size 30,000 expressions that are showing up here. That would get us to here in the next one. How can there be size 30,000 expressions at 100 steps when this, oh, this is the differences.
Right, differences there.
So this is a messy one. It's funny that that isn't yet visible in, let's kill that. Okay, so I'm really getting very hungry here. The other case, okay, so this is going to give us, okay, that's the length 9 ones. And now if I say, combinator fixed point list. So what I want to do is I want to find the ones that have not terminated after a certain period of time. So do we have that combinator terminated queue? Yes, and that uses the standard evaluation. Okay, so if we say combinator fixed point queue, max size, okay, so then we say, What we want are the ones that do not terminate. So what we want to say is pick, actually we've got here, all S9 is that thing. We want to pick from all S9 the result mapped onto all S9. Do you believe that?
Sounds good to me. So this is a 100th anniversary of Combinators.
It's about to be.
Yeah. It's worth pointing out when you give your talk on this that you've got, what, hundreds of trillions of times more power than they had back then.
Indeed, but why didn't this work? What did I do wrong? Combinator fixed point. Is this right? Combinator terminated Q? Does that do what I think it does? Mano, that would be a question for you.
Yeah, you put in the expression. I think that should work.
But is it only doing it with respect to? No, that's just completely wrong. Oh, no, it isn't. No, it isn't. That's whether it actually terminated, right? That's whether there are no matches available, right?
Yeah.
Okay, so wait a minute. Combinator fixed point. Let's just try looking at that. Okay, whatever. Well, let's just do this. Let's just run the combinator fixed point over all of those. Okay, let's get that run. And now, okay, I mean, that looks harmless enough. So there are some there, that's interesting, that there's some that probably terminate after one step that are just like that. Okay, so that looks harmless enough. So now why did, some of these ones down here one would think was non-terminators. So let's go combinator terminated Q on %189. Okay, I don't understand this. Let's try running the one we know doesn't terminate. Well, here, any one of these would be fine to run. Wait a minute. That peak down there is these failure objects. See what I'm saying?
Mm-hmm.
I bet that's what's happening here. Okay, so what we want to do is we want to say if it's a failure, what's the second argument of enclose is to do the okay. All right, so then what we want to do here is we want to say combinator terminated queue I've confirmed there, not combinator terminated queue, enclose true ampersand. Okay, so then this should give a whole mixture. Oh. Okay, fine. So now we want to say pick all S9 %194. Okay, so this is the first set of potential, interesting ones that don't immediately terminate. Okay, so let's use our scheme from before where we generated so this should be hopefully why is this so slow? Huh, why is this so slow? Oh, I just ran. Okay, fine. Okay. Seems to be taking a while to render this. Okay. So this is for the size 9 ones. So the question is are these wilder? Let's see what kind of thing we see here. I should have fixed that bug. Actually,
and maybe add the plots that we've been using over and over.
Yeah, what are they? I mean, they're just longer versions of the same thing.
Is there a differences plot? Oh, okay, there is. Okay.
Yeah, we've just been using longer ones. I mean, but we could take. Okay, hold on. Let me just fix this bug. Where is it? Where's the depth thing? I don't know how useful these are. What do you think about these? I mean, these are amusing, but I don't think they're that useful, these DAG plots. Let's skip to DAG plot. Okay, now let's try running this. Let's try going to max size. At least, let's try 5,000 and let's go this one to 500 steps. And let's say this thing here, depth is wrong. I need to do heads goes to true. Should we, here's a good start. Let's do list step plot here. And I wonder whether we want, okay, let's run this. And while we're at it, let's correct this to being list step plot. And I think we want to make this by default differences. Oh, you know what? I had another bug there, which I want to fix. Wow, that one looks cool. That one looks really cool. Let's make another, let's fix another potential mistake here. Do you think ratios is useful, or should we skip ratios?
I think it can be skipped. Oh, well, except when it points out something.
Well, then let's not skip it. It's not taking a lot of time. You know, what was taking forever was those plots. Okay, so now let's save these in. Okay, so there's a whole bunch of these that look quite wild. Okay, so some we've seen, like these ones we've seen before. Oh, and you know what I should have done, actually, before I even, let me fix this in one way. Which is to say, take these things, line 196, and let's say combinator evolve list hash comma 5, and then let's say select that leaf count hash double equals 9, and then what I want to do is I want to say lost of each of those, and then I want to do union of that, I claim. Because what that's doing is getting rid of ones where, okay, 141, okay, so that's getting rid of transients, that's the point. That's getting rid of ones where, did you get what I'm saying?
Mm-hmm. And that way they'll have more distinctive behavior.
Yeah. Okay, let's get rid of this. Combinators 41S9 summary. Let me save over that. Okay, let's look at these. So I think the best indicator that we have is the differences column. This is the total depth. I think that one isn't going to do anything very exciting. Let's look at the ones that look promising in terms of being wild. That one looks somewhat promising.
Looks repetitious to me, though.
Yeah, okay, fair enough. I agree. Okay, well, let's look at the ones that look the most convincing. I think that one is non-trivial.
Mm-hmm.
Let's try that one.
Nope, that's going into counting.
Okay. I should have added the plot range to all there. What about that creature? I think that's going to be repetitious, but I'm not certain. Let's try it for a little bit longer. I think that's similar to the one we saw before that seemed complicated, that was an SK one.
Yeah, I agree.
Yeah, that one looks promising to me. Let's try going to 200,000. So we can kind of cut it down to size, but again, I'm thinking it's that is non-trivial, I think.
Oh yeah.
Okay, let's look at this one here. What's that doing?
The 16 looks like it's counting, but it has a really huge transient before it. Yeah, that's definitely regular.
Okay, look at this puppy. This puppy looks promising.
Nope, that's definitely a fractal behavior of some sort.
Okay, what about this guy? What do you reckon?
Don't know. That's definitely going to be in the complicated category.
Yeah, we've seen one very much like this before.
Yeah, almost identical, in fact. Let's see, and your thing for where you eliminated things in 9, is there any chance that things could have gone down as far as 8?
Sure, I'll check that. Okay, so let's do an S9 survivors play. Well, nothing appears to have gone down to 8.
Okay.
Just check 7. Nope, I don't think so.
Okay. Because this one looks much like one we looked at before.
No, I agree. The thing I'm surprised by, what's this guy doing? That's super regular. Let's take a look at that. Hey, wait a minute. Why are there K's in here? Wait a minute. What are we looking at here? S9 survivors. Why are there things with K's in there? I'm going to have to go in a moment. But drat. Something went horribly wrong here. S9 survivors. What happened here? Those are all S's. I wonder how big these are. They're even the wrong size.
Try doing a search on K in that notebook.
Well, these are size 8, so something has gone horribly wrong here. We've just got the wrong data here. Okay, S9 survivors. How long is S9 survivors? Okay. And then here, oh, look, length of GGGX.
Ah, I see.
Why is it saying part 47 of that does not exist? Oh, this is the problem.
Oh, right.
In fact,
S9 survivors?
yeah, in fact, all the data was correct. Drat. Well, all this data was correct. It just had the wrong. Here, I'll just run this again. And I need to go in a moment here. Okay, so this is Okay, so the basic point is this was correct, but we'll have to run these things again. But the fact is, but the expressions we had to represent them were not correct.
Right.
That's annoying. Well, I think there are going to be some non-trivial ones here. That guy looks promising. Maybe that's going to get simple again. Yep, presumably. I need to go. Well, to be
Interesting stuff.
Well, Ed, are you around a bit later? Because I would love to go on with this.
Sure. I'm not doing anything.
Okay. Well, maybe we can, and I'll leave.
Yeah, just send email or something.
Yeah. Okay. I will. Oh, look at these.
Is this still live?
Yeah, we are. But we'll wrap that up. Okay. Well, we've got more to. Sorry, guys, on the live stream. We're the most exciting discoveries might be made offline. It's all right. We'll record them anyway. Look at that guy. Oh, that one looks promising. Boy, this is such a weird business. You know, I have to say, this is what I've been doing all my life. Basically, is this hunting for interesting creatures. And you know, it's just the question is only whether the hunting apparatus is improved. And we do have slightly. Oh, look at that guy. I think that's not as trivial as you think. I think that has some interesting variation.
Mm-hmm.
Okay, I'm going to send you, Ed, for this notebook, and actually, could Mano, could you send Ed the Codo 2 as well?
Will do.
Okay. All right. Well, thanks.
Don't have your spectacular 12-course dinner now.
No, I'm not. I'm going to have something to eat because I'm really hungry. It's not a very 12-course, I assure you. All right. Well, thanks everybody, and thanks to folks on the live stream. If anybody survived here, and